Welcome back to the deep dive. Today we are putting away the plans for the next residential veneer and stepping into a world where standard construction materials simply vaporize.
They really do.
If you're listening, and specifically if you are a Canadian Masonry apprentice, you've probably mastered the fundamentals, the running bonds, the perfect plumb, the structural block work. You're feeling confident.
And that's exactly the foundation we need. You've learned the rules of the road for building stable, attractive, weather-tight structures. Today, however, we're going to bridge the gap between that conventional knowledge and a completely different discipline.
Refractory Masonry.
Refractory Masonry. Think of it as moving from, say, the general infantry into the Special Forces branch of our trade.
I think that Special Forces analogy is spot on. It really is. Because it immediately highlights that this work operates under totally different rules. It demands far greater precision and a very specialized knowledge base. Our mission today is to use the very standards and textbooks you're currently studying, the Canadian Masonry curriculum, to introduce you to the high-heat industrial world. This is where material science dictates everything, and frankly, it's where you find some of the highest pay scales.
And the most resilient job demand in the industry, for sure.
Absolutely.
The skills you'll learn here, they transform you. You go from a builder who's concerned with load and aesthetics into, well, an engineer focused on thermal containment. This isn't just a niche field.
Yeah.
It's a whole career trajectory that involves maintaining the very backbone of heavy industry across North America.
So let's start with the defining term, the foundation of this entire deep dive, refractory. What does that word specifically describe in terms of materials? What are we talking about here?
Okay, when we talk about refractory materials, we're talking about specialized compounds. Usually they're very high in things like alumina or silica, and they possess this incredible ability to withstand extreme temperatures.
And we're not just talking about a hot day.
No, not at all. We're often talking about temperatures exceeding 2,000 degrees Celsius. And critically, they have to do this without suffering any critical failure.
So it's not just about not melting.
Exactly. They cannot weaken, they cannot melt, they can't soften. They must not lose their fundamental structural integrity or, their chemical composition under that immense thermal stress.
That is a staggering contrast to standard masonry goals. I mean, when we lay conventional concrete block or clay brick on a commercial project, what are we thinking about?
You're thinking about structural stability, weather resistance.
A 50-year lifespan, maybe? And definitely the curb appeal?
Right. Standard masonry goals are built around a relatively stable ambient environment. Refractory goals, they're fundamentally hostile.
Hostile. That's a good word for it.
The goals are containment, thermal resistance, and most importantly, defense against an onslaught of chemical and physical wear that is happening continuously inside the vessel. You aren't just building a wall.
You're building what? A shield.
A sacrificial thermal defense shield. That's what we call the hot face, or the working lining of a furnace.
And because these materials are so critical to industrial function, I imagine the job demand for people who can actually install and repair them is massive.
It's huge.
If an apprentice wants to find where this work is, which sectors should they be looking at in North America?
The industrial landscape is hungry for skilled refractory masons. We can kind of break down the major sectors into a few groups. The first group comprises the foundational heavy industry.
The big stuff.
The really big stuff. The processing plants for iron and steel. So blast furnaces, coke ovens, steel ladles, all massive, complex refractory structures.
And the scale of the work itself is often intimidating, right? Just because of the sheer size of these installations.
Precisely. The second major grouping would be non-ferrous metals processing.
Okay, so that means metals that don't contain iron.
Correct. We're talking nickel, copper, and aluminum processing plants. And these environments, they have their own unique chemical wear challenges. Molten aluminum, for instance, is incredibly corrosive and requires very, very specific refractory solutions.
And then there's the third enormous category. This seems to cover nearly every other product and industrial function that needs intense heat.
The third group, it covers everything from petrochemicals, producing oil, gasoline, and fuels, to heavy industrial products like glass, cement, and lime.
Cement kilns are notorious, I hear.
Notoriously tough on refractory linings. And you can't forget the power generation sector, heat treating furnaces, large coal-fired power plants, and even nuclear facilities.
It's important to note, though, that while you might see commercial jobs like, say, large incinerators for hospitals or older industrial smokestacks.
Right, they exist.
They provide a much smaller, more sporadic volume of work compared to the massive cyclical maintenance demands of the heavy industrial sectors you just listed.
That is a crucial point for anyone planning their career. The long-term employment stability is found in those large industrial sites that are constantly cycling down for maintenance.
So to help everyone visualize what we're talking about maintaining, let's briefly describe the typical refractory structure we work on, the vessel anatomy, if you will.
Sure.
How is a high-heat vessel typically built, say, from the outside in?
Okay. A refractory vessel is basically any enclosure designed to contain intense heat. And it's almost always built from the outside in. You start with a rugged outer steel casing. That's the primary structural element, and it's usually built by boiler makers or fabricators.
And then inside that structural casing, what's the next layer?
We usually have an insulating layer. This is designed to hold the heat in, maximizing the vessel's thermal efficiency. It protects the outer steel shell from overheating.
Is it always there?
In some lower temperature vessels, or if the client is maybe prioritizing capacity over insulation, this layer might be omitted, but generally it's there.
And finally, the part where we spend all our time, the inner lining.
That is the hot face, the working lining. This is the crucial sacrificial layer. It has to be strong enough to withstand the direct chemical and physical assault from whatever's being processed, the molten metal, the slag, the intensely hot gases, while protecting the more expensive insulating and structural layers behind it.
So the selection of materials here is everything.
It's key to the vessel's operational life, absolutely.
Okay, that makes sense. Let's transition into Section 1 then, the core mission material science for extreme heat. You mentioned the working lining is sacrificial. This is where we have to stop thinking like residential masons.
Whoa.
We have to start thinking like materials engineers.
Absolutely. We need to define something called refractory value or refractoriness. This is the specific property that dictates the material's ability to resist high temperatures without losing its mechanical strength. It's not enough for it just not to melt.
It has to do its job while it's hot.
It must still bear its load and resist chemical attack, even at 1500 degrees Celsius.
And the standard for measuring this isn't just a simple thermometer reading. We use a very old, specialized system, the pyrometric cone equivalent, the PCE number.
That's right. The PCE test is foundational in our trade. Pyrometric cones are these small, standardized, numbered masses of refractory materials, specifically manufactured in a cone shape.
So they're like little test pyramids.
Kind of. They're placed in a furnace and heated at a steady, specific rate. The PCE number assigned to that cone corresponds to the temperature at which it softens under its own weight and deforms to touch the base.
Okay, but why is this method preferred over just sticking a thermocouple in the furnace to measure the melting point? What's the advantage?
Because it's a direct measurement of the material's functional strength under heat, not just its theoretical melting point. It measures a combination of temperature, time, and atmosphere. For a mason, this is much more useful.
Because that softening is the failure point.
That softening under load is the moment of critical failure. If the material can't hold its shape, the entire structure collapses. The PCE scale ranges from the coolest, which is 022, all the way up to 42, which is the hottest.
And that number is directly linked to performance in the field. Precisely.
If we look at a common high-performance material like silica brick, its PCE is typically 32-33. That means it deforms between 1710 and 1730 degrees Celsius. That PCE number is the language we use to specify the correct material for a given furnace environment.
Now, let's talk about the constant state of war these materials live in. Beyond simply resisting the peak temperature, the lining has to endure a whole variety of stresses. This is our enemy list.
Yeah, the wear mechanisms that destroy the vessel from the inside out. The most immediate stressor is thermal cycling.
Thermal cycling.
This is the unavoidable consequence of industrial operation. Repeated heating, which causes expansion, and cooling, which causes contraction of the vessel. Think about a steel ladle that's filled with 1600-degree molten metal, then emptied, then allowed to cool significantly before the next pour.
That constant movement, that flexing, must be absolutely brutal on the lining.
It is the primary cause of refractory failure. This movement leads directly to what we call thermal spalling.
Spalling. That's the cracking and breaking off of the surface.
Exactly. The cracking, crumbling, and breaking off of the lining material, which reduces its thickness. If the material we select can't handle that repetitive stress, the vessel's operational life is just drastically cut short.
So we're battling physics, but we're also battling physical assault.
That's where abrasion and erosion come in. Abrasion is the mechanical wear caused by hard solids in direct contact. So maybe hard metals moving through the vessel or high-velocity particulate matter just rubbing the lining away.
And erosion, is that different?
It's similar, but erosion is typically caused by dynamic liquids, molten metals, or more commonly, slag. The constant movement, the flow, or the agitation of these liquids physically washes away the lining material over time.
You mentioned slag. Let's address the chemical attack, corrosion.
Right. Slag is the fused waste product from ore processing, and it is highly reactive. It often contains chemical components like iron oxides, lime, or fluxes. Corrosion is the chemical attack where the slag actually penetrates the refractory material, dissolving the internal bonds and leading to deterioration.
So choosing a brick that resists the specific chemistry of the client's slag is paramount.
Absolutely. A mason working on a lime kiln needs a completely different lining chemistry than one working on a steel ladle. It's that specific.
And finally, we have to account for simple physics. Load.
Yes. Load is the bearing of excessive weight. If you're lining a massive structure like a tall blast furnace or rotary kiln, the sheer weight of the refractory material itself becomes a massive stressor.
Especially when it's hot.
That's the key. It's especially true because refractory materials can slightly soften at extremely high temperatures, which makes them much more vulnerable to deformation under load.
It sounds like instead of designing a building to be permanent, we are designing a lining to resist an unstoppable force.
That's the engineering of managed failure. You're selecting and installing material designed to fail slowly, predictably, and consistently. By doing that, you maximize the time between expensive shutdowns.
And that leads directly to the core reality for any apprentice entering this trade. Refractory work is overwhelmingly about repair and maintenance.
Absolutely. You might spend a small part of your career on new construction, but the vast majority is high-pressure, time-sensitive maintenance during scheduled plant shutdowns. The systems are designed to be cannibalized and repaired.
Our source materials note that some high-stress vessels, what was the example?
A large rotary cement kiln. It might need significant repair or replacement cycles as often as twice a year.
Twice a year. So the goal isn't to build it once and walk away.
Well,
The goal is to execute a precision repair under tight deadlines so the facility can get back online and start producing product again.
because downtime costs massive amounts of money, often millions of dollars per day. Refractory masons are essentially the trauma surgeons of industry, rushing in to fix critical damage before the patient bleeds out financially.
That sets a perfect stage for Section 2, refractory bricks and specialized mortars. For the standard mason, this looks familiar. It's a brick. It's a trowel.
But the function is radically different, starting with the composition. We call these refractory bricks Firebrick. And while they look superficially like the clay bricks you're used to, their core differences are in composition, primarily their alumina content and the required installation precision.
Let's run through the grades of fire clay brick. This is foundational knowledge. The simple rule is the higher the alumina content, the higher the refractoriness and temperature resistance, right?
That's the key metric. The source material categorizes 4 primary grades based on their ability to resist heat, starting with the most economical, low-duty brick.
Okay, low duty.
This grade withstands temperatures up to about 1520 to 1595 degrees Celsius. You'll see these used for backup linings, often behind a hotter face layer or in lower temperature applications like certain stacks or ductwork.
So it's a supporting player usually, stepping up to medium or intermediate duty.
This grade pushes the range up to 1640 to 1680 Celsius. They're common in moderate temperature stacks, ash pits, and ash hopper linings in boiler service. They offer slightly better resistance to abrasion than the low-duty grades, making them a good, cost-effective workhorse.
Then we hit the heavy lifting requirements with high-duty brick.
High duty. This is where things get serious. It dramatically increases the resistance, handling up to 1690 to 1745 Celsius. This material is designed to resist that thermal cycling we talked about, that constant expansion and contraction.
Which makes it essential for
Or things like steel ladles, blast furnace linings, or ceramic kilns where the process requires frequent heating and cooling cycles.
And finally, the top tier of fire clay, Super Duty.
Super Duty takes us slightly higher in temperature, up to 1745 to 1760 Celsius. But the key advantage here isn't just the few extra degrees of heat resistance.
What is it then?
It's the enhanced resistance to both thermal cycling and chemical corrosion. This makes Super Duty essential for the most aggressively harsh environments, like rotary kiln linings and soaking pits where the environment is chemically hostile.
So that's the fire clay spectrum.
Hmm?
But industrial hellscapes, as you call them, often require us to go beyond fire clay and look at specialized materials engineered for specific assaults.
This is where that alumina content becomes absolutely critical.
When the alumina content climbs significantly, say between 48% and 99%, we move into the high alumina brick category.
Right, and these materials can withstand temperatures up to 1870 degrees Celsius. What's fascinating here is that the high purity of the alumina dramatically increases resistance to all the major wear mechanisms: slagging, spalling, and vitrification.
Vitrification. That's where the material starts to turn glass-like, right? High alumina bricks resist that process well.
They do, which is why they are often used in areas exposed to heavy slagging, such as electric furnace roofs, iron ladles, and the transition zone of cement kilns, where you have both high heat and serious chemical attack present.
Then you have materials that are chemically specific, like silica brick.
Silica brick is nearly pure silica, derived from quartzite. It resists high temperatures, around 1700 C, but, and this is a big brigus, but it is extremely sensitive to thermal cycling.
So you can't use it in a batch furnace that starts up and shuts down frequently.
It would spall almost immediately. It's reserved exclusively for steady-state, high-heat operations, glass tanks, coke ovens, certain roof sections, where the heat remains constant for long periods of time.
And when the primary enemy is chemical attack from highly reactive slag, you need those heavy metal-based refractories.
That's when we turn to chrome and magnesite. Chrome brick, high in chrome ore, offers exceptional resistance to chemical slag, and it can handle heat up to a staggering 20-40 degrees Celsius.
Wow, where would you see that?
You'd find it in certain metal containment vessels and recovery boilers in chemical environments, like in paper mills.
And magnesite, made from magnesium oxide, is similar in its resistance profile.
Yes, magnesite resists erosion extremely well, with a maximum service limit of 1800 C. It's a staple in cement kilns and metal holding furnaces, where resistance to that physical and chemical scrubbing is paramount. The material selection is half the job.
You have to be a detective.
You really do. You have to figure out exactly what chemical cocktail and heat profile the vessel's going to see.
Let's discuss the physical building blocks themselves. Refractory masons use specialized brick shapes to build the curved, cylindrical structures found everywhere in industry.
Yeah, unlike the standard modular units in residential work, industrial refractory relies on 4 essential shapes. You have the straight brick, which is your standard rectangle. But for curves and arches, we need tapered shapes.
The arch, wedge, and key.
Exactly. The arch brick is tapered on the header faces, the wedge brick is tapered on the stretcher faces, and the key brick is tapered on the bed faces. These 3 tapered shapes are crucial for installing perfectly self-supporting arches and rings in round or cylindrical vessels.
Which are the backbone of most industrial furnaces.
They are.
And we have to acknowledge the persistent North American reality here. Even though we're a metric country, the standard refractory straight brick dimensions are 229 by 115 by 76 millimeters.
Which we all just call a 9 by 4.5 by 3 inch.
Right. Industrial settings, particularly older plants, often dictate that we work in this metric-imperial duality. Apprentices have to be comfortable converting and reading prints in both systems instantly.
It's just part of the job.
Let's talk about mortar. This is a massive departure from the lime, sand, and cement mixtures of standard masonry. We're moving into chemical and ceramic bonding territory.
Fundamentally different. Refractory mortar is finely ground refractory material, often crushed firebrick, and it must be chemically matched to the brick being laid. Silica mortar for silica brick, high alumina mortar for high alumina brick, and so on.
And we categorize them not by strength class, but by how they achieve their final bond.
Right. We start with heat-setting mortars. This requires the apprentice to completely rethink how masonry sets.
How so?
Heat-setting mortars are typically shipped dry. The crucial point is that they achieve little to no strength until they are exposed to very high temperatures, typically between 1100 and 1370 degrees Celsius.
So until it gets hot, the joint is fragile.
Exactly. The structure relies entirely on its mechanical stability and the quality of the bricklaying until the full burn-in process happens. The ceramic bond is the final permanent bond achieved only by that intense heat.
So the strength isn't there immediately. Contrast that with air-setting mortars.
Air-setting mortars are more convenient. They're formulated to form an initial chemical bond just on air exposure, whether they're shipped wet or dry. This gives the lining immediate handling strength.
And that bond holds it together until
the vessel reaches high heat, allowing the permanent ceramic bond to take effect and surpass the chemical bond strength. This makes them much more versatile for complex installations or areas that won't see the highest peak temperatures.
Now let's talk about the installation process itself, specifically joint thickness. This is where standard muscle memory needs a radical correction. In residential work, a 10 mm joint is normal.
Standard, yeah.
What is the standard in refractory work?
This is the single biggest discipline shift for an apprentice. Precision is king because the mortar is the weak link. A refractory mortar joint must be approximately 1 millimeter, and under no circumstances should it exceed 2 millimeters.
So if you're laying brick with a 5 mm joint,
You are installing a guaranteed point of failure. It's that simple.
why is that thick joint so detrimental in a high heat environment? What's actually happening?
It's because the mortar and the brick, even if they're chemically matched, have different thermal expansion and contraction rates. If the joint is too thick, the excess mortar material will expand and contract at a different rate than the brick mass.
Which creates stress.
It causes thermal stress to concentrate right on the edge of the brick, leading to almost immediate spalling and joint failure under thermal cycling. The tight joint distributes the expansion stress across the entire brick unit, not just the interface.
That makes perfect sense. So how do you achieve that consistently thin 1 to 2 millimeter joint? You can't just butter it like you would standard brick.
No, we typically use the lubrication method, which everyone in the trade simply calls dipping. Instead of spreading the mortar with a trowel, the mason dips the entire bed and header faces of the brick into a pan of thin, soupy refractory mortar.
Dipping. You compared it earlier to buttering toast, where you spread a thin, uniform layer.
Yes, it ensures the mortar layer is thin and uniform. The brick is dipped and immediately set into place. It's a fast, high-precision technique, and crucially, in refractory work, once you set the brick, you cannot disturb it.
You can't tap it into place.
If you try to adjust it after the initial set, you break that fragile bond. You have to scrape the brick entirely clean and re-dip before setting it again.
It sounds like speed and accuracy trump aesthetics entirely. We're not tooling these joints for visual appeal.
Not at all. Appearance is irrelevant. Accuracy is paramount. A clean, tight 1 millimeter joint is beautiful to a refractory engineer, regardless of how it looks to a residential client.
We spent a lot of time on bricks, but many modern linings use very few or no bits at all. Let's transition now to Section 3, the monolithic materials casting and ramming.
This is the ultimate departure from traditional masonry.
Monolithic refractories, from the Greek meaning single stone, are formed in place as one continuous unit, minimizing joints.
And joints are the inherent weak points in a lining. The two main types we use are castables and plastics.
Let's dive into castables, which are essentially high-performance refractory concrete.
That's a great way to think of them. They are specialized concrete formulations, shipped as dry granular blends, ranging in bag size from 25 kilograms up to large 3,000 kilogram super sacks. They're composed of refractory aggregate alumina, bauxite, things like that, and a chemical binder, often a high-alumina cement.
This sounds familiar to pouring concrete, but I get the sense the storage requirements and contamination risks are far more severe.
The storage is crucial. Castables must be kept dry and warm. The ideal temperature for mixing water and storage is between 13 and 24 degrees Celsius because temperature dramatically affects the set time. But the absolute site rule is contamination control.
And the contamination we worry about most is standard Portland cement.
Yes. Portland cement or even plaster dust can cause what's called flash setting.
Flash setting.
The material hardens prematurely, often within minutes. This immediate hardening prevents the proper formation of the chemical structure, dramatically weakening the castable's ultimate refractory strength. Any equipment mixers, shovels, wheelbarrows that has touched Portland cement must be exhaustively cleaned before mixing castables.
Let's discuss the installation methods, starting with the simplest conceptually, pouring.
Pouring castables uses formwork, typically steel forms, which are essential for strength, especially because we rely on vibration for consolidation. When you're pouring vertical walls, the form panels are generally limited to about 1.2 meters in height to manage the hydrostatic pressure of the dense material.
And we have to consolidate this material, just like concrete, to eliminate voids, especially around those critical anchors.
Consolidation is non-negotiable. You achieve density either through mechanical vibrating or through manual puddling for less critical applications. When you're vibrating, the rule is to hold the vibrator vertically, letting it penetrate the layer under its own weight, generally 300 to 400 millimeters deep.
How long do you vibrate for?
Only long enough to see the material slightly glisten and flow. You have to watch it carefully.
Because over-vibration is a danger, too. What happens if you vibrate too long?
If you vibrate for more than 5 minutes, you risk segregating the components. The heavier aggregates settle, and the lighter components and excess water float to the surface. This creates a weak layer, which leads to failure during burn-in. Precision and timing are everything.
The sensitivity to water volume is notorious. How does a mason check consistency in the field for, say, a general-purpose dense castable?
We use the ball and hand test. It's simple but effective. You take a handful of the mixed castable, compact it into a ball, and then toss it about 30 centimeters a foot into the air and catch it.
And what are the 3 possible results? What do they mean?
Okay, so if the ball remains completely intact but adapts slightly to the pressure of your hand-like, slightly dense dough, it's perfect. That's the ideal plastic consistency.
And if it's too dry?
If it crumbles and falls apart, it's too dry. That's dangerous because it risks poor placement and high porosity.
And too wet.
If it flows or slumps through your fingers, it's too wet, which guarantees weakness and low density after setting.
And we really need to emphasize the risk of insufficient water, especially with modern mixes. Why does too little water risk delamination after burn-in?
With low and ultra-low cement castables, which are common now, insufficient water means the hydration process, the chemical setting, doesn't complete properly. When that material is fired during the burn-in, the internal bonds haven't formed correctly. This causes the material to separate into horizontal layers.
To delaminate.
It delaminates. And these low cement mixes are so sensitive they often require warm water, 21°C or higher, to ensure that complete fast hydration and mixing are achieved due to their finer particle size.
Let's move to the second installation method, gunning, or gunite. This involves spraying the material onto the surface.
Gunning uses a dry gunning machine. Because you often can't use traditional full formwork in complex geometries or large repair areas, masons rely on shot boards.
What are shot boards?
They're temporary wood planks or metal forms cut to the desired lining thickness. They just act as a guide for the nozzle operator to maintain a consistent layer against the backup surface.
The process involves pre-dampening the material before it even enters the machine. Why is that step so critical?
For gunning, the material is pre-dampened with 3 to 5% water by weight. This is crucial for controlling dust, a major health hazard, and for significantly reducing rebound.
Rebound, that's a material that bounces off the wall.
Exactly. It's the material that bounces off the wall during spraying. If you have too much rebound, it gets trapped in the fresh mix, leading to layers with low density and lamination problems. Pre-dampening helps the material flow through the hose and reduces that wasted, compromised material.
So the final water needed for the set is added at the nozzle itself.
Exactly. The material travels dry to the nozzle, where water is pumped in via a water rink. This puts immense pressure on the nozzle operator.
So they're controlling the mix in real time.
They are. They must continuously monitor the water flow, ensuring a fine balance. The 2 primary pitfalls they have to avoid are too much rebound or slumping.
What causes each one?
Too little water means too much rebound material bouncing off and being trapped, causing low density and lamination. Too much water means slumping. The material just sags on vertical walls or overhead applications.
So there's a specific technique for applying it.
The nozzle operator uses a large looping motion, holding the nozzle about 1.2 meters away at a 90-degree angle to the surface. And they always start by gunning the bottom edge first to form a shelf that supports the material above it.
This precision skill is intensified when we talk about hot gunning repairing a lining while the furnace is still operational.
Hot gunning is one of the most high-risk applications in the trade. It avoids costly complete shutdowns. But since the furnace is often running at white-hot temperatures, the radiant heat is immense.
How do they even get close?
The nozzle operator works from a distance, extending the gun nozzle with a long pipe that can be up to 6 meters long. They wear specialized heat-reflective suits, often made of aluminumized material, and tinted drop-down shields to prevent eye damage from the intense light and heat.
And the work schedules must be incredibly rigorous due to the heat stress.
They are non-negotiable. Masons work in short, intense bursts, usually 5-minute shifts, followed by a mandatory break to rehydrate and cool down. Teams just cycle through continuously.
There's a counterintuitive detail here. During hot gunning, they often add more water at the nozzle than normal.
They do.
Why add more water when the environment is so incredibly dry and hot?
Because the intense ambient heat causes the material to hydrate and set much faster than normal, which leads to failure. The extra water is used strategically to slow the hydration process, ensuring the castable can be applied and consolidated before the heat bakes it instantly.
The third method is shotcreting, often reserved for larger high-volume jobs.
Shotcreting is the most technologically advanced of the monolithic applications. It's similar to wet gunning, but utilizes a specialized low-cement castable optimized for pumping via a high-pressure swing valve pump. The equipment is heavy, so it requires a larger crew.
And what's the primary benefit of this specialized system?
Control. Unlike dry gunning, where the nozzle operator controls the water visually, shotcreting uses a precise flow meter. It removes the guesswork entirely. Water volume is controlled precisely from the pump truck, ensuring maximum density and consistency.
And they use a chemical additive as well.
Yes, they rely heavily on a set accelerator, a chemical agent added at the nozzle, which speeds the setting process, giving the material almost immediate mechanical strength upon impact. This is essential for overhead or vertical work, where gravity is an immediate enemy.
That brings us to the other major monolithic category, plastics. These are the highly moldable, stiff materials that come pre-moistened.
Right. Plastic refractories are stiff, moldable, and already contain all the necessary moisture. No water is added on site. They have physical or chemical qualities similar to refractory brick, but they're used for forming difficult shapes or executing high-quality, dense repairs.
Like what?
Like firebox repairs or lining intricate molten metal applications. For instance, alumina graphite plastics are prized for their non-wetting properties in contact with molten metal.
And the installation method is the defining feature here. Ramming.
Ramming is physically intense. The plastics arrive in large slugs, often pre-divided into smaller manageable slices called clots. Installation is a two-person team effort. One mason places the clots against the form or the wall, and the second uses a pneumatic air rammer to compact them.
We need to stress the hard rule for layer thickness when ramming.
The rule of 60 millimeter. No more than one layer, or 60 millimeters, about 2.5 inches, may be laid at a time. This rule is absolute.
And what happens within that layer?
Each 60 millimeter layer must be rammed with the pneumatic rammer until the individual clots meld together into a dense, solid, unified mass.
And to ensure that one 60-millimeter layer bonds properly to the next one you put on top.
After ramming one layer to full density, the top surface has to be intentionally roughened, usually by raking, scoring, or chipping it. This roughened surface ensures proper mechanical cohesion with the next layer of plastics placed on top.
And that prevents what?
It prevents the entire lining from delaminating horizontally when the structure is fired up.
What about protecting hardware, like the anchors that hold the lining to the shell when you're hitting the surface with an intense pneumatic rammer?
You have to use dummy anchors. These are temporary false anchors, often made of wood or some expendable material, that are placed where the permanent anchors will eventually go.
So you ram around the dummy.
You ram the plastic material right up to and around the dummy anchor. Once the material is compacted, the dummy is removed, leaving a perfectly shaped, dense void where the real anchor can then be seated without being damaged by the ramming process.
Finally, let's briefly mention ramming mixes, which are similar but drier than plastics.
Ramming mixes have a lower moisture content than plastics. They're more like granular particles, and they're rammed to achieve extremely high density. This high density provides exceptional resistance to abrasion and corrosion, making them highly suitable for the most severe environments.
Such as?
Such as the bottoms of aluminum smelting furnaces or high wear zones in metal holding vessels. When we're ramming these mixes, we compact vertical walls to a depth of 50 to 75 millimeters per layer.
This transition from standard block to ramming plastics in 60-millimeter increments truly demonstrates why refractory is the high-skill branch. It all comes down to the extreme precision required.
It does.
Which leads us perfectly into Section 4, precision, expansion, and complex structures.
And we have to reiterate that foundational rule, the tight joint requirement. A refractory joint is 1 to 2 millimeter maximum. To the residential mason, this seems impossibly tight.
And it forces you to use high-quality, extremely accurate bricks that conform almost perfectly to dimension.
Exactly. And you explained it earlier. This extreme precision is required because a thick joint would fail under thermal cycling due to those differential expansion rates between the mortar and the brick.
The quality of the lining work dictates longevity.
Sloppy joints guarantee early failure. The brick laying must be immaculate because the thin mortar is merely the glue, not the compensatory cushion.
Now let's confront the fundamental physics of extreme heat, managing thermal expansion. The materials are going to grow, and if that growth isn't managed, the lining will crush itself and the steel shell.
Thermal growth is unavoidable. Fire clay and aluminum materials expand less than silica, chrome, or magnesite, but all expansion must be accommodated, otherwise the lining becomes unstable. We primarily use two methods for managing this.
Method 1, expansion joints.
These are planned, unmortared gaps designed to absorb that material growth. They are typically spaced 1,500 to 4,000 millimeters apart. And it's absolutely essential that these joints are kept completely free of stray mortar.
What do you put in them?
They're sometimes filled with a compressible ceramic fiber or an alternate insulation material that can be compressed as the refractory lining expands.
And in vessels holding liquids, I understand these joints are often hidden.
Yes. In ladles or vessels holding molten metal, expansion joints are sometimes strategically located in corners or beneath wall seats to prevent molten liquids or highly reactive dust from seeping into the joint.
And if it seeps in?
Seepage into the joint compromises the insulation and can cause localized catastrophic failure.
Method 2, loose joints, which sounds contradictory to everything we've just said about tight joints.
It does, but loose joints are spaces left in the head joint, the vertical joint, but not the bed joint. We create this space intentionally by placing a thin layer of combustible material, like thin paper or cardboard, between the bricks as they are being laid.
And what happens when the furnace is fired up?
The paper or cardboard burns off cleanly during the initial heating. This leaves a small, uniform gap. As the refractory lining heats up and expands, it slowly closes that gap, allowing the bricks to achieve a tight, mechanically stable bond against each other.
So it's a temporary spacing mechanism designed to facilitate controlled expansion.
Exactly.
This process of achieving full bonding and removing moisture is called the burn-in process, which is perhaps the most critical controlled step in the entire construction and maintenance cycle.
The burn-in, or dry-out, or bake-out. It's the managed heating schedule that brings all heat-setting materials, mortars, castables, and plastics to their full design strength. The schedule is typically a detailed engineering document managed by the contractor or supervisor.
And it absolutely cannot be rushed.
Rushing the burn-in is catastrophic. The furnace has to be heated very slowly at a regulated rate, usually 25 degrees Celsius per hour. This slow rise ensures that moisture is driven out gently and that the ceramic bonds can form completely and uniformly.
And then you hold it at temperature.
Right. That setting temperature must then be held, or soaked, for at least 48 hours. If the material heats too fast, the moisture trapped inside turns to steam and literally explodes the lining apart. If the material freezes before burn-in, it loses all structural strength.
Let's look at a prime example of complex precision work. The rotary kiln. This is a massive spinning cylinder, presenting some very unique installation challenges.
Lining a rotary kiln, which is essentially a giant cylinder lying on its side, is extremely specialized. We lay the bricks in continuous rings. One method is the rotating method.
The rotating method.
Masons lay the lining in the bottom half of the cylinder, and then the kiln is slowly rotated to allow them to lay the next section.
How do you prevent the bricks from falling out when the kiln rotates?
They have to be temporarily secured. This is done with specialized fast-setting high-temperature glues, or more commonly, with mechanical screw jacks that are tightened between an arch form and the brick ring to hold them firmly against the steel shell until the entire ring is completed and self-supporting.
But if the client can't rotate the kiln, there are specialized mechanical support systems.
Yes, the pogo stick method is famous. Masons use spring-loaded support bars, the pogo sticks, that temporarily press individual bricks against the kiln shell or the inner arch form. These bars maintain constant pressure until the full ring has been keyed in and becomes structurally stable.
It sounds highly physical.
It's highly physical and demanding work.
And then there's the modern mechanized approach.
That would be the pneumatic ring machines or pneumatic bricking machines. These are mechanized support systems that project outward from a central arch form, applying uniform pressure simultaneously to all bricks in a ring. They significantly reduce the manual labor and time needed for temporary support,
while ensuring the highest quality, most stable ring.
Exactly.
Finally, let's talk about the critical structures that hold the lining to the steel shell against erosion, vibration, and thermal shock, anchoring systems.
Anchors are vital. They mechanically secure the lining, preventing it from collapsing or bulging outward. The choice of anchor material is critical because the tip of the anchor is often only 25 millimeters from the hot face. It has to be an alloy capable of withstanding the operating temperature of that part of the lining.
For monolithic castables, we typically use metallic anchors.
Yes, typically V anchors or sometimes Y anchors for very thick walls or dual lining applications. For high-temperature plastic refractory linings, especially those seeing temperatures above 1600 C, we have to move to ceramic anchors.
Ceramic anchors or refractory tiles?
Right. And these are held in place by metal C-clips or scissors clips that grip the back of the anchor and are welded to the steel shell.
And just like the bricks, we must accommodate the expansion of the metallic anchors themselves.
We do. Before installation, metallic anchors are often coated with wax, bitumastic paint, or fitted with plastic caps. During the burn-in process, these coatings melt or burn away cleanly, leaving a small, controlled allowance. A gap for the anchor to expand or move without cracking the surrounding rigid refractory material. This prevents the anchor from becoming a localized stress point.
For massive, heavy walls, anchors alone might not suffice to support the weight. We need wall seats.
Wall seats are crucial for heavy, tall linings. They are steel plates mounted on brackets welded to the shell, and they serve as sectional support. They minimize the potential for the lining material to slump due to gravity before it's fired, and they reduce the extreme shear force exerted on the anchors themselves.
And you often align expansion joints with them.
It's common practice to align horizontal expansion or control joints with these wall seats to manage the stress flow.
This complexity is why the safety stakes are so high, bringing us to Section 5. High stakes environment safety and demolition. This trade demands professional-grade safety protocols.
The work environment is intrinsically hazardous, and apprentices must be ready for the reality of working in confined spaces.
Which means restricted access and high risks related to lack of oxygen, dangerous dust, or gas buildup.
All masons must be thoroughly trained in the employer's confined space procedure. This includes continuous atmosphere monitoring to check for explosive gases, toxic substances, or oxygen depletion. And absolutely critical is the lockout-out procedure.
Lockout-tagout ensures no unexpected energy release occurs while you are inside the vessel.
Correct. Before entry, all energy sources, electrical, hydraulic, gas, compressed air, must be disconnected, locked out, which means a physical lock is placed on the switch or valve and tagged with the name of the worker responsible.
It prevents the unexpected startup of machinery
or release of hazardous energy while workers are inside the vessel performing a repair. It is a life or death protocol.
The dust factor is another massive concern, particularly regarding inhaled carcinogens, especially silica dust and refractory ceramic fibers, or RCF.
This is one of the dirtiest, highest-risk trades when it comes to respiratory health. Masons are constantly exposed to silica dust, mineral wool, and refractory ceramic fibers. RCF is particularly dangerous due to its extremely fine, fibrous nature, which is a known respiratory carcinogen.
The non-negotiable solution here is PPE and strict adherence to regulations.
You must follow all government regulations, OHSA, WHMIS company policy, and the manufacturer's specification for personal protective equipment. This includes specialized filtering respirators and understanding the handling requirements for fibrous materials. In this trade, taking shortcuts on dust protection is simply not an option.
We discussed hot gunning earlier. That's the prime example of working under conditions of extreme heat.
Beyond the heat-reflective suits and tinted shields, working in extremely hot environments demands rigorous protocols to combat heat stress. This includes mandatory, specific hydration protocols, regulated shift schedules, those short 5-minute bursts,
and comprehensive first aid training
that specifically addresses heat exhaustion, heat stroke, and treatment for inhaled chemicals, especially gases produced during a hot process.
Refractory masons are often responsible for removing the damaged lining, the demolition phase, before they can even start building. How do we determine where the old lining is failing?
Inspection is the first step. During shutdowns, masons look for signs of damage, cracks, excessive spalling, or thinning surfaces. Sometimes damage is detected during operation by observing hotspots. Areas where the exterior steel shell is glowing red, indicating a complete failure of the refractory and insulation layers inside. Thermal imaging devices are also often used during shutdowns to detect subtle temperature variations that the naked eye might miss, identifying early-stage deterioration.
And safety must remain paramount during removal.
Absolutely. When removing a lining, especially an arch or a tall wall, temporary load-bearing supports braces, screw jacks, or wedges must be installed before demolition begins, and their minimum required strength must be calculated by the supervisor.
And protecting the area.
The surrounding area must be protected from falling debris and dust using barriers, tarps, and specialized containment systems.
What are the main methods for actually breaking out the old material?
Dense brick, castables, and plastics are removed using heavy equipment pneumatic or hydraulic hammers and pneumatic chisels. Smaller areas can be chipped out with hand tools. An increasingly common method, especially for removing debris that's clinging to the steel shell, is hydrojetting.
High-pressure water.
Extremely high-pressure water to break up the material. In operational furnaces, specialized tools like ceramic welding lances can be used to thermally cut through the damaged area.
The removal of fibrous materials presents a unique set of hazards that require different techniques.
Yes. When removing mineral wool or ceramic fiber products, the primary goal is fiber containment. For ceramic fiber, thorough wetting prior to removal is strongly recommended, as the moisture suppresses the fibers from becoming airborne.
And you can't use power tools.
Critically, you must only use hand tools, scissors, or utility knives for removal because power tools dramatically increase the release of harmful airborne fibers.
And the final step, waste management and cleanup.
All waste material has to be bagged immediately. The site must be thoroughly cleaned, and specific equipment must be used for dust control. A HEPA-filtered vacuum is essential for final cleanup to ensure carcinogenic dust and fibers are contained and not recirculated.
And disposal is regulated.
Disposal of ceramic fiber and mineral wool must adhere to strict federal, provincial, and local regulations due to their hazardous nature.
We have covered the materials, the physics, the specialized installation methods, and the intense safety requirements of industrial refractory masonry. Let's circle back to what this means for the apprentice listening.
This is a demanding branch of the trade, requiring a higher level of discipline and material knowledge than standard masonry. But understanding this transition makes you a highly specialized and extremely valuable tradesperson.
Let's summarize the critical points of contrast they need to internalize.
Okay, first, the core objective changes. Refractory work is about extreme thermal resistance and containment against corrosion and abrasion. It is not about aesthetics or standard load bearing.
Second, material selection.
Material selection is based on chemistry, the alumina factor and the PCE number, dictating whether you use a low-duty fire clay or specialized materials like chrome for slag resistance.
Third, the precision is extreme.
Brick joints must be 1 to 2 millimeters, which requires specialized techniques like dipping over conventional buttering.
And finally, mastering the monolithic methods is essential.
Yes, this means understanding the water sensitivity and consolidation requirements for castables, avoiding flash setting, and the physically demanding method of ramming plastics in controlled, thin layers.
All while managing thermal expansion through strategic expansion joints and slow, controlled burn-in schedules.
All of this requires specialized training, particularly regarding safety in confined spaces, heat stress mitigation during hot gunning, and absolute zero-tolerance compliance with dust control. But in return,
The payoff.
refractory masonry is characterized by excellent career longevity, consistent job demand during industrial maintenance cycles, and generally superior compensation due to the high skill level required.
The takeaway here for you, the apprentice, is that you are transitioning from construction to engineering. In standard masonry, you design structures meant to survive a stable world. In refractory work, you are facing a truly hostile, unstable environment.
And that is the provocative thought I want to leave you with. When you select a refractory material, when you decide that a chrome brick lining is necessary over a high-alumina lining, you are making an engineered choice. You are selecting a material that has been chemically designed to combat a specific, high-risk combination of heat, physical erosion, and chemical attack.
You're not designing it never to fail.
You're designing it to fail slowly and predictably under the most hostile, aggressive conditions on Earth. The refractory mason is not just a builder. They are an engineer of managed failure, pushing material science to its absolute operational limits every single day.
A perfect way to frame the challenge and the career waiting for you. That was the deep dive into refractory masonry. Thank you for joining us.